So, Jai Hind to all of you. I am Dr. Sulekha Saxena, Assistant Professor, EC Department, Ajay Kumar Garg Engineering College, Ghaziabad. Today, we will continue the topic instruction set of 8085 microprocessor. We have already discussed the instruction set, and as we know that there are 5 types of instruction sets in 8085 microprocessor, and in previous lecture we have already covered data transfer instructions. So, now moving to forward, we will cover up the arithmetic and logical instruction group in this lecture. So, first of all, in arithmetic operation, 808 performs only 4 basic operations, that is addition, subtraction, increment and decrement. Since 8085 is a 8-bit microprocessor, so most of the instructions performed by 8085 includes 2 8-bit numbers and it performs the addition on 8-bit number. The result will be 8-bit and will be stored by default in accumulator. So, if we have to perform 3 plus 2 for example, then one of the input will always be from accumulator and we will specify the second input, either it should be from register or memory location or immediate data. So, by default 8085 performs arithmetic operation with accumulator, that is first data will always be in accumulator and second data will be specified either using registers for register addressing mode instruction or through memory location using indirect mode instruction or through immediate data, that is immediate mode instruction. So, moving forward, the first addition instruction is add. Both the contents can be registered, that is R1, add R means add accumulator with register, or add M means add accumulator with content of memory location. So, here only one operand will be specified, that is either R or M, and the second operator will by default be through accumulator. The content of register or memory location are then added to the content of accumulator and result will be stored in accumulator. So, for example, if we talk about add B, then the instruction will add the content of accumulator plus B register and store the result in accumulator. Since both the operators are in register, so this instruction will be of register addressing mode. And since no data or address is specified, the size of instruction will be of 1 byte only. The machine cycle will be only one, that is opcode fetch, and will be of 4 T states. So, this is the overall detail of this instruction. If we take another example of memory location, that is add M, since the memory location address is pointed by HL pair, so the content of address specified in HL pair is added to accumulator and the result will be stored in accumulator. So, in this way addition instruction will work, that is by default it adds the second operand value to accumulator and store the result in accumulator. In all the arithmetic operations, flag register will be modified. For example, if we take accumulator 04, C register B05, then after execution, that is add C, the result in accumulator will be 09. Similarly, if we take accumulator 04 and HL pair will contain 2050 and the content of 2050 is 10, then this instruction will add 10 plus 4, 14, which is equivalent to E. So, the result will be 0 E. Sorry, the result will be 1 4 only. Now the second instruction is ADC. This instruction adds accumulator plus register oblique memory location plus carry flag to accumulator, that is add with carry. So add register or memory location with carry flag to accumulator. Rest all the operation will be performed in the similar way. For example, if we take an example ADCC, then let the accumulator value will be 50, C register 55 and carry flag 1. So after the execution, the result will be 55 plus 1, that is 56. Similarly, if we take another example of ADCM, carry flag 1, accumulator 0 fix, and HL will contain 2050. Let this address has value 30, so the result will be 30 plus 6 plus 1, that is 37. And this value will be stored in accumulator. So in this way, this instruction ADC will get performed. The third is ADI, that is add immediately 8-bit data to accumulator. This instruction performs the addition of accumulator with 8-bit data specified in instruction to accumulator. So let before execution accumulator contains 03, and if we run ADI 05, then 05 is added to accumulator value, that is 3, and the result of accumulator will be 08. ACI means add immediate data with carry flag to accumulator. So accumulator plus 8-bit data plus carry flag is saved to accumulator. For example, let before execution carry flag is 1, accumulator is 5, and if we perform ACI 20, then it adds 20 plus 5 plus 1, that is 26. So 26 will be available in accumulator after execution. In all the previous 3 instructions, add, ADC, ADI and ACI, the data, both the data are of 8-bit only. DAD is only instruction which performs addition on 16-bit data. So DAD add given register pair to HL pair and stores the result in HL pair. That is, value of HL pair plus register pair is added and stored to HL pair. For example, if we write DADD, it adds HL plus DE and store the value in HL. So L plus E, that is 5 plus 4, 9 and 3 plus 4, 7. So L will contain 79, and H plus D, that is 3 and 5. So H will contain 35 after execution. So by default it adds L plus E and store in L, H plus D and store in H. So this is the way DAD instruction will work. Now moving towards subtraction operation. In subtraction also similar to addition, first operand will always be in accumulator. The second operand will either be through a register, through a memory location or through immediate data, and this instruction will subtract second operand from accumulator and stores the value to accumulator. So by default first operand will be in accumulator and we have to just specify second operand in instruction. Let subtract R or M. In this case, this instruction will subtract register or memory value to accumulator and store the result in accumulator. For example, if we write subtract C, this instruction will subtract C from A and save the result to accumulator. So before execution, let accumulator is 09, C register is 04. So after execution, the value will be 9 minus 4, that is 05. If we write subtract M, then memory location will be pointed by HL pair. Let HL is 205 0. So the instruction will move to 2050 location, fetch the 10 data, subtract it from the accumulator. 14 minus 10, that is 4, will be saved to accumulator. Next is SBB, that is subtract with borrow. So this instruction subtract accumulator minus second operand, which will be in register or memory location, minus carry flag, which contains borrow, and save it to accumulator. So let carry flag is 1, accumulator will contain 8 and C register will contain 5. So SBBC. So 8 minus 5 3, 3 minus 1 2, so accumulator will contain 0 2 after execution. Similarly, we write SBBM and let HL pair contains 2050 and the value at 2050 location is 02. So this instruction will do accumulator minus content of memory location minus carry flag, 6 minus 2 4 minus 1 3. So the accumulator will contain 0 3. So this is how subtract with borrow work. Now with immediate data, that is subtract immediate data from accumulator. So this instruction will subtract the 8-bit data specified in instruction from accumulator and saves the result to accumulator. Let accumulator contains 08 and the 8-bit data specified is 05. So the instruction will perform 8 minus 5, that is 03, will be stored in accumulator. This is SBI, subtract immediately given 8-bit data from accumulator with carry flag, with borrow. So this instruction will subtract 8-bit data given in instruction and carry flag from accumulator and store the result in accumulator. For example, if the carry flag is 1, accumulator contains 25, then SBI 20 will perform 25 minus 20 minus 01, which is equal to 4. So the after execution, the result will be 4. Now the next are increment and decrement operation. It is quite similar to addition and subtraction, but increment means just +1 and decrement means -1 simply. So the content of register or memory location is specified in instruction is incremented or decremented by 1 using increment or decrement operation, and this operation can be performed either on 8-bit data or of 16-bit data. To perform 8-bit increment or decrement, we have INR and DCR. Similarly, to perform 16-bit increment decrement, we have INX or DCX. So let we talk about increment. So increment can be either in register or in memory location. So INRR or INRM. In both the cases, the content of register or memory location will be incremented by 1. For example, let B register contain 10 and if we run INR B, so after execution B register will become 11. Similarly, if we talk about INRM and let the content of HL pair is 2050 and the content of this location is 10. So after execution, the content of this particular location will be increased by 1, that is becomes 11. So hope this increment operation is clear to all of you. In the first case, the register value is only updated and we will not go into any memory location. So the instruction size will be of 1 byte only. The machine cycle will be only 1 opcode fetch and the T states are only 4. Whereas in the second instruction, since there is no address or data specified, so size will be 1 byte only. But we are reading data from memory adding 1 and again saving it to memory. So there are 3 machine cycles: opcode fetch, memory read and memory write. So the total T states will be 4 plus 3 plus 3, that is 10 T states. So there is a quite difference in timing of both the instructions, whereas both the instructions perform only plus 1 operation. So the INR R will take only 4 T states, whereas INR M will take 10 T states. Now moving towards 16-bit increment or decrement. For this purpose we use INX, INX R or INX M. Here INX R means INX register pair, and 16-bit data will be stored in register pair only. So INX will be added, the operand will be register pair, and register pair can be BC, DE or HL. So we can either write INX H, INX B or INX D. D means DE, B means BC and H means HL. So the content of register pair will be incremented by 1. For example, if we take INX H, before execution the content of HL pair is 10 and 20. So after INX H, the content will be updated to 1020 plus 1, that is 1021. Similarly, if we talk about decrement, there are 2 operations, 8-bit and 16-bit decrement. DCR means 8-bit decrement. So decrement register or content of memory location by 1. For example, if we write DCR E, the content of E register is 20. So after subtraction, the content will be 20 minus 1. Since it's a hexadecimal value, it will not be 19 but it becomes 1F. Since it's a hexadecimal value, so 20 minus 01, the base of this number system is 16. So we have to take borrow, which comes out to be 16. 16 minus 1, 15, which becomes 1 F, and 1 minus 0, 1. So the result will be 1F. Next is DCRM. Let the content of HL pair is 2050, so it will move to the memory address 2050, and the content of this location is 21. DCR will reduce it by 1, so the content of 2050 location will become 21 minus 1, which is 20. So hope DCRE and DCRM are clear to all of you, and similar to INR, these both instructions are of 1 byte only, but it takes more time because it has to read and write to memory location. So this instruction will be of 10 T states, whereas DCRE is of only 4 T states. Next is 16-bit decrement, that is DCX. Using DCX, we can decrement 16-bit data by 1, and for 16-bit data we use register pair. So similar to INX, at DCX, the register pair can be HL, BC or DE, and it reduces the content of register pair by 1. Let we write DCX H. Before execution, let HL pair contains 1021. So after DCX H, the content will be 1020. So previous are some of the all the arithmetic operations, where only 4 arithmetic operations are there in 8085. For arithmetic operations, plus, minus, increment and decrement are only specified. Now we move towards logical instructions. In case of 8085, the following logical instructions, that is AND, OR, XOR. I hope you all know about these gates. We have already discussed it in digital system design. For AND gate, it performs the AND operation between both the inputs. When both the inputs are 1, only then output is 1, else 0. For OR gate, it performs logical addition or logical ORing of both the inputs. If any one of the input is 1, output will be 1. And XOR will perform the logical XORing of both the inputs, that is, when both the inputs are exclusive, that is different, output will be 1, and when both the inputs are same, output will be 0. So it will perform AND or XOR. Also it performs rotate, compare and complement. So these are the 6 operations which are performed in logical instruction group. And in case of AND or XOR, both the data are of 8 bit and data can be specified either in register or using memory location or 8 bit immediate data. So when we perform AND operation A and A, by default first operation data will be in accumulator and we will provide second data either in register or in memory location. So it will do the AND operation between accumulator and register or memory location and stores the result in accumulator. So this instruction will perform the AND operation between accumulator and content of register or memory location and save the result in accumulator only. Here, two important things need to be noted, that only sign, 0 and parity flag will be modified after AND operation and carry will be by default reset and auxiliary carry will be set during AND operation. So let we use A and AB. Accumulator will contain AA and B register will contain 0F. A means 10, so accumulator becomes 8 and 2 10, 8 and 2 10, and F means 0F means this value. So after ANDing of accumulator and B register, it becomes 0 0 0 0 1 0 1 0. That is 0 and 8 plus 2 10, which is equal to A. So after AND operation, the result of accumulator will be 0A. Since we are performing this operation, so the carry flag will be reset and auxiliary carry will be set. Remaining all other values, sign flag will be 0 since MSB is 0. Since there are even number of ones in data, so parity flag will be 1. And since there is non-zero result, so 0 flag will be 0. So this is the value of overall flag register in after AND operation. Similarly, if we talk about A and AM, let accumulator contains 55 and the HL pair contains 2050 and at this address data is B3. So 55 means 0101 0101, B that is 11, so 1011 and 3 that is 0011. If we perform the AND operation of this value, 0001 then 0001, which becomes 1111. So after this operation, the accumulator will contain 11, carry flag will be set and auxiliary will reset and auxiliary carry will be set. Also, now I hope you all can calculate the value of other 3 flags, sign, 0 and parity. Since MSB is 0, sign 0, result is non-zero, 0 flag 0 and result contain even number of ones, so parity flag will be 1. Next is AND with immediate data. So AND accumulator with 8-bit immediate data. So accumulator and 8-bit immediate data is directly ANDed and the result will be stored to accumulator. Also the flags will remain the same, that is sign, 0 and parity will be modified, carry and auxiliary carry will be reset and set respectively. So let we perform A and I3F. Before execution, let accumulator contains B3. So B means 11, that is 1011, 3 that is 0011, 3F 0 0 1 1 and F means 1 1 1 1. When we perform AND operation, it becomes 0 0 1 1 0 0 1 1, that is 3 3. So the result of accumulator will be 33, which is stored in the accumulator. Also carry flag will be reset and auxiliary carry flag will be set. By seeing this data, we can find out that sign flag will be 0, 0 flag will be 0 and even number of 1s, so parity flag will be 1. Moving towards OR operation. We all know that OR, logical OR operation means logical sum of both the inputs. If both the inputs are 0, output will be 0, whereas if any one of the input will or both the inputs are 1, output will be 1. So here also the content of second operand, that is register of memory location, is ORed with accumulator and result will be stored in accumulator only. So OR operation between accumulator and register or memory location will be saved to accumulator. Sign 0 and parity are modified, whereas carry and auxiliary carry flag both are reset to show the result. So let accumulator contains AA and B register contains 12. So A, that is 10, so 1010 1010 and 12, that is 001 0010. When we perform ORing, it becomes 1 0 1 1 1 0 1 0. So this is the result. 8 to 10 1 11, that is B and A. So result after execution will contain, accumulator will contain B, A, and both carry and auxiliary carry flag will be reset. Similarly, ORAM will perform the logical operation between accumulator and the content of memory location. So let accumulator contains 55 and content of memory location will be 3. So it performs similar operation, that is 1 1 1 1 and 0 1 1 1. So it becomes F7. The result of accumulator will be F7 and both these values will be reset. This operation will perform OR with 8-bit immediate data, that is logical ORing, and similar to OR operation previously, it do the OR operation between accumulator and 8-bit immediate data and save the result to accumulator. This is the similar example that we have previously discussed, that let accumulator contains B3 and immediate data is 08. So result will be 1 0 1 1 1 0 1 1, that is B B, and both the flags will be reset. Next is XOR operation. XOR is simply exclusive OR operation between accumulator and register or memory location and save the result to accumulator. Here also carry and auxiliary carry will be reset, rest all the things will be same. So I hope you can easily see the operation of exclusive OR. Let accumulator content is AA and C register content is 2D. So it is 1 0 0 0 0 1 0 0 1 1 1. So it is 8 and 7. When both the inputs are same, output will be 0, and both the inputs are different, output will be 1. So result is 87 and both the flags will be set. XRAM will perform similarly. XRI 8-bit immediate data, it performs accumulator and XOR with 8-bit data to save the result in accumulator. So till this point, we have covered all the 3 gates. Next is compare operation. Compare operation basically compares both the inputs, will not save the result anywhere, it will only update the flags. So if we talk about compare R or M, it do the subtraction operation, that is A minus R or M, but will not save this result, rather update the flags based on this result. Carry 0, let accumulator is greater than R, then carry will be 0, 0 flag will be 0. Let accumulator equal to R, then 0 flag 1, carry will be 0. And if accumulator is less than R, then carry 1 and accumulator 0. So the content of operand is compared with accumulator. Both the contents will remain the same and only flags will be changed. So let we take an example, compare D. So it will perform A minus D. That is 10, accumulator is 10 minus 20. After execution, the content will remain the same. But since A is less than R, so carry flag will be 1, 0 flag will be 0. So carry and 0 flag are used to show the result, and remaining all flags will get modified. This instruction will compare accumulator with 8-bit immediate data and do the analysis in similar fashion and update carry and 0 flags only. Rotate instruction will rotate the data of accumulator either through left or right direction. RLC will rotate accumulator to left without carry flag. Let the accumulator data at B0, so B7. So RLC will rotate, shift the data B0 to B1, B2 to B3, similarly B6 to B7. B7 will be updated in carry flag and also to B0. RRC will do this towards right side, that is move the data from B7 to B0. B0 will be updated in carry flag and also to B7. RAL will move the data to left with carry flag, that is carry is in the loop, this B7 is moved to carry and carry will be moved to B0. And similarly RAR will move to right, that is B7 to B6, then B0 to carry flag and carry flag to B7. So this is the overall rotate operation. Last is complement. The content of accumulator will be complemented using complement. So if we use CMA, it will complement the content of accumulator and save to accumulator only. And CMC will complement the carry flag. STC will set the carry flag. So these are all the logical instructions. So in this lecture, I have covered both the arithmetic and logical instructions set of 8085. And in next video, we will cover the remaining, that is branching and machine control group. Hope you have quietly and clearly understood all the instructions of 8085. Thank you.